So we've already seen what a linear model looks like, but now we need to understand how we actually estimate the parameters beta 0 and beta 1 to go into that model. So how do we do it? So this scatter plot here of our data is actually really, really important. So you can imagine that there might be a bunch of different lines that could fit through this data. So I could imagine one fitting through here. I can imagine one that's got a bit of a lesser slope here. One that's a bit steeper might roughly fit through this data as well. So how do we know which model is the best model, which is the best line to fit through there? So having some definition of what best means would be a good start. So let me start by drawing in one particular line, which fits through the data here. So it's got an intercept of beta 0 and a slope of beta 1 is the idea. And now what do we mean by best? So we need some measure of the distance here of each of these points from our line. So the definition that we'll take is we'll say the vertical distance between each point and the line there, that's the distance that we want to minimize. So what is that distance? Well, we can write it down as it's going to be the distance from my point, yi, from this line itself. So that's going to be subtract beta 0, subtract beta 1, xi is the equation of my line. And now, obviously, this is going, for this particular point that I've drawn here, this is going to be negative because yi is less than, is underneath my line here. So really what I want to do is I want to square these. And then what I actually want to do is I want to count up all of these different distances from each point to the line. So all of those different distances there. And I really want to minimize the sum of each of those. So from I equals 1 to n, ei squared, that's going to be the sum from I equals 1 to n of all of these differences. So if I can minimize this sum here, this cost function, then that actually gives me the parameters beta 0 and beta 1 of this line which minimizes the total distances, which is the best fit to the data. So how do we do that? Well, if you know any calculus, you can maybe imagine differentiating this function with respect to beta 0 and beta I, setting the derivative equal to 0 and finding local minima and maxima that way. If you don't remember calculus, then that's fine. The results turn out to be my estimate of the best fitting slope here turns out to be the covariance of the x's with the y's divided by the variance of all of the x's. Then once I have that, I can calculate the intercept as well, an estimate of the intercept here, beta 0, and that turns out to be y bar, take away beta 1 hat, so my estimate that I've just calculated, times x bar, so the sample mean of the y's and the sample mean of the x's. The good news is you don't actually need to go and do this calculation every time you want to fit a linear model. R does all of this for you, and so that's what we're going to talk about next.